you can give it to everybody else by uploading to the folder, and you can pull the code down. Everything I'm talking about is already written there, so you can pull that down, those files down, and this slide down. All right. And this is just the philosophy, okay, that I want to make Python accessible to everybody. That's one of my main philosophies. Make data science in general accessible to everybody. The classes are meant to be dropped in on if you want, where you can actually, spend a lot of time to think about what we're doing and learn, do a regular study of the languages that we use for data science. Okay. So I'm a big believer in the rubber and the road. I'm going to walk you through some basic exercises, and again, try and follow me and maybe get this code up and running on your own machine. If you don't have a machine, partner with somebody who's next to you. That'll facilitate, and then I want to leave you with a set of tools that you can actually develop from, and then we'll build out the rover example. So. All right, so in case you don't know what Anaconda is a distribution of Python and a lot of things that you need. It makes it very easy to get a lot of consistent packages on your machine very quickly. So, so if you don't have it installed and you're not ready to go, I suggest you go to Continuum.io, downloads, and you can get the Mac, PC, or Linux installer. The one caveat I should say about this is when it tells you there's a non-default path setting, so it'll say, would you like to set paths? And it's not default, it's not selected. You always want to set paths with this package so that the paths are mapped to all the pieces and your computer knows where to find everything that's on. If you guys have any questions about this setup or anything I say, since we have a little bit of time here, you feel free to ask. Because I want everyone to be on the same page. Okay, so once you get your Jupyter Notebook set up or your Anaconda set up, you can either click on, you'll have one of these guys, which would be your Anaconda browser, right, or launcher. It gets called Anaconda Navigator. Sometimes it puts it right on your desktop. It has all the pieces, right? Console, Jupyter, which is the notebook, Spatial, which is an IDE we won't use, but you can use that. Or you can just open up your bash, right, your command line, and type in Jupyter Notebook or Jupyter Lab. Jupyter with a Y, and that'll launch your notebook, and then you can actually just write Python the way I'm going to do it today. So, quite cool. Once you open your Jupyter Notebook, you'll see a setup like this, right? So this is Jupyter Lab, it's a little different, but the idea is that you have code cells. So the thing that's really nice about the notebooks is you can write notes in Markdown. You drop this down, you can get Markdown code, and then you can write notes in codes, and it interprets the code, right? So if I want to dissect a piece of code, I have the code in the cell on top, and then the code in the cell on the bottom. I can actually take pieces and test them out without infecting the cell on top. So you'll see me do that, but I just wanted to introduce this button and the idea of cells. And I believe it's a little not rendered that well, but this would be a Markdown cell because you see it has text, and then you see how there's some sort of coloration here. That's your code cell. Forgive me if this is really basic. I just want to make sure everybody's on board. All right. Okay, yeah, there's that code thing right there. Okay, so the problem, right? So the problem that I think is really fascinating is that an organism or a rover, anything that has its own intelligence in its exploring environment needs to have a strategy, right? And the really cool thing about this Python code is we can write this modularly. We can write the mechanics of the rover, right? We can write the mechanics of the environment, and we can write the mechanics of the intelligence. And we can make each of these a different module and swap them out in and out. So that's what I'm going to set up for you. But let's go back a little bit, back to biology. This is sort of the motivation for this. and think about this little soil worm called C. elegans. So I did a PhD in biology, and I studied this worm for my PhD in biology. And this worm has a task, right? It has to navigate the environment. Usually it's sort of in mud, right? How does it navigate the environment? It smells gradients. And the question is, like, what does it do behaviorally to do this in an intelligent way, right? So it's got basically two behaviors, maybe three. But one of them is running, going forward, right? It kind of looks like a snake, not really one. And the second one is what we call pirouetting, where it turns to a random degree, right? So there's sort of a random degree to where it turns. And we could just think about that in terms of that. Now the thing it wants is salt. So if you look at this is like an experiment. This is where they put the worm down, and this is where they put the salt down. So the task it's going to want to do is go in the most efficient way to that salt, right? How does it do that? And it turns out that what happens is, if you see the concentration per time, right? So as this you could think of as the gradient, right? And the positive values here are it's going up the gradient. Negative values are it's going down the gradient, and the zero is it's running along the gradient, right? So what happens is the probability of pirouettes, probability of turns, when it's going down the gradient, it just randomly turns around to different degrees, and then it senses the gradient change. And when it's going up the gradient, it suppresses all turns and it goes straight. So you can see that behavior here. Sort of there's a probability of pirouetting. Pirouettes because it's actually running along the gradient, nothing interesting is happening. Then you can see this really long run, right? And it sort of taxes over to here, and then it actually starts going down the gradient, and the pirouette happens again up here. And it ends up relatively effectively getting to that point. So to bring this all back to what we're talking about, right? This is a real-world search strategy, very simple one, right? Probability of pirouettes, random turn, and run, right? It's very simple, basic things. The question is, can we code this, and can we make a rover or a robot or something like that do this in an intelligent way? Log back on here. And if this does interest you, this isn't the only search strategy, right? There are a lot of search strategies. There's huge literature on this stuff, so you can really dig into this type of algorithms. And I think it's a really great way to model intelligent behavior, if that's what you really want to do. Okay, so here's my setup. Here's what I'm going to do. Python has a plotter called Turtle. I don't know if you guys are familiar with Turtle. You might have been familiar with Turtle from the 80s. It's like one of the things you learn from basic, right? It's an XY plotter. Hey, it's Andrew. That's Andrew over there, everybody. If you have any questions at all, he knows all the answers. All right. So Turtle is the XY plotter. I'll introduce you to Turtle. We can basically model any drawing behavior, any driving behavior, and keep tracks, right? Keep tracks of what's going on. So that's kind of cool. It's like fossilized behavior. And now we'll develop a strategy to submit commands. So we'll develop a strategy to submit commands to Turtle automatically. Then we want to move Turtle, right, according to those commands. This may seem very basic, but I really like pseudocoding like this because I don't know how much, if you guys code, like sometimes you get confused, right? Sometimes you get stuck on something, confused, maybe you don't even realize you're confused. This pseudocoding keeps you straight, right? Even though it seems very basic, very protected. Add a nice background, okay, so maybe we make it a little more realistic. And then maybe have it draw a shape, that we drive, right? So can we drive the turtle? And then this is what I was talking about before. Can we modularize this for easy iteration? Once we do that, we're ready to go. And that's actually where I want to get you guys to. I build out all the mechanics, we modularize it, we have a slot for the intelligence, we can drive it, right? And then let you go and think about what kind of algorithms you want to introduce. So change the search strategy module. First, we'll start with a random tumble. I'll code that for you guys. And then maybe have the ability to import a list of obstacles, right? So then we start to enrich the environment, actually have a virtual environment. And then the thing that I think we should do is you can build a simple reinforcement learning paradigm, right? So maybe add some obstacle avoidance code, add some look forward code, like where are you going to go? Do you have an internal map of that area? Do you have an estimate of what that area might look like, right? So those types of questions. And then do you have a plan, right? What's the plan? What's the behavioral plan? If you see an obstacle, if you don't see an obstacle, or if there's an unknown, right? So we could think about trading off an exploration versus a avoidance behavior, right? Rates of exploration. So all these things must be very familiar to you if you're interested in AI, the learning rate, the exploration rate, the avoidance, the negative weight on the avoidance for negative outcomes, right? So, okay, and then I'm going to let you guys go, right? And let you guys code this stuff and pull down the notebook and just build out the notebook. And, you should be able to, I think, with the way I've set it up, you should be able to make some sort of intelligent behavior in your code. Let's see. And you can share your code. Right now, I have that folder that's linked to my webpage. There's supposed to be a blog. In the future, the blog function should be there. So it's like a place where you can keep on going, and hopefully there's new ideas that come out and posted. So I make this available to everybody. And if you do cool stuff, it'd be really cool if you could put some back on there. All right, cool. And here's some more ideas, right? Obviously, swapping new algorithms. Maybe you want to make some introspection method to figure out what's inside the brain of your AI, right? Is the map growing? How is it growing? Maybe do some time series. Change color of the track to reflect the rover's internal status, right? One very simple idea is if it hits an obstacle, it turns red. You can do that. And then I'm sure you guys have other ideas. Yeah, and then here's the turtle. They call it turtle because I guess it started as a turtle. I don't know, you always see these old icons of turtles. You can try to change it to something else. And here you see the state right here. So it's issuing commands and producing commands in that output. One thing I should say about the code is it's written in tkinter. Anybody know about tkinter? Anybody know what tkinter is? Yeah.
Yeah, it's like it's like a GUI.
It's for building GUIs, yeah. Anybody have any feelings about tkinter? Or?
It's hard to use.
It's hard to use, right? Does anybody know why it's hard to use? This is actually important because it affects the demo. Single thread. You guys know what single threading is? Yeah. So it runs on a single thread, which means it takes over the whole console, it takes over everything, and it only runs that window. So it locks everything else down, right? So in order, you'll see when you run this code, you'll see your code will lock up. The way to stop it from locking up is you pull the window up again and close it, right? Sometimes you have to kill the kernel, which is the Python kernel. Hopefully that doesn't happen with the code that I've written, but those are the two things that end up happening sometimes with tkinter. Yeah, I say that right here. All right. Cool. So I like this guy, right? He's really good at doing workshops. So this is sort of what I'm going to do, and then I'm going to release you guys to like make more trees. So that's the idea. All right. So from here on out, I've got all the stats, and I'm just going to go through the notebook with you guys with all the pieces, so you can understand everything that's going on in this piece of code. I'm going to bounce back and forth because I kind of have to get my hands on the machine. All right, so the first thing is basic list of commands, right? So we need to be able to issue a basic list of commands, either from our AI brain or from our driving system, right? Run the drive. So, and then we want to be able to iterate through the list of commands, right? The pop statement, anybody know what pop is? Right, so we've got to have a list, which is one of these stacked objects, and pop will decrement the list. Yeah. Why is pop cool? Yeah.
Cross stuff off your students.
Yeah.
Pop reads a statement and then it crosses off.
Yeah, destroys it, right? So your list gets decayed, and if you pull that list up again, it's in the state where you left it. So it's a very convenient way to have a list of commands in there. Good. So let's do that. I'll pull my notebook up. So you should, if if you've got Anaconda up, you should be able to, well, first of all, this is the folder that's available to you. Again, it's a little ugly, but it's a Google Drive folder. It's on my website here. You should be able to get it right here, AI over Meetup, so that'll link directly there, and you can actually drop stuff in as well. Put your name on it or something, so it doesn't overwrite or stuff, because you have full access. And then if you are interested in this stuff and you want to join the email list, I do send out emails, whenever I'm giving a workshop or whatever. So there's that. And then onto the code.
File solution.
Question?
Yeah, you want us to use the file installed virtual rover solution.
Yeah, that's just the walkthrough. That's got it's got none of the questions and all the answers. I didn't know that there. Yeah. So the question is actually at the end. It's the part where you build it out more. All right. So let's see if I can get this so it's clear.
Copy this.
All right, so the first part is over here. So I'm going to just probably highlight from here. So the idea is that we have a command list, right? So tkinter works, or Turtle works with actual commands, like word commands. So the first thing is just to demonstrate the function of pop. And again, if this is basic, forgive me, I want to make sure everybody's on board though. So this is one of the basic Python objects. It's a list, it's got order and sequence. And as I pop, I can pop off these different items. And so basically it's print the command list, print this pop 1, we're popping from the, let's see, this would be the 0, 1. Okay, well, that's kind of weird. But anyway, I probably should, you can specify which item to pop from, right? Which sequence item to pop from, so we can do that. So, do that. And you can see how the pop works. So basically, pop 1, that's 1, 0, 1, 2, 3, 4. Pop 1, pop 1. You can see how the list is declining. So we can use this to issue commands to Turtle, right? Go forward, go backwards. Anybody think about the next step that we might want to take?
Add commands?
Mm-hmm.
Add commands?
Which ones?
Add new commands?
Yeah, we could add new commands, definitely. We could sample, right? Yeah. Yeah. Or we could evaluate those things. Yeah. So let's do that. So here's another one. So in this case, we were just passing through these strings over here. So we can pass the strings with a value, right? So in this case, forward 25, left 5, forward 100, forward 10, and then quit. And this over here is a while loop, right? So we have to initiate the movement string, and then while movement string is not equal to quit, right? So you can actually run this until this thing is until this thing reaches quit, right? And then we can print out the command just to see. I like to do that first, just to make sure that we have the commands being issued the way we want them to be issued. Okay, so you can see that it's working. It's got the commands marked through. I was told to go forward 25, I was told to go left 5, and so forth. So let's actually make it do something, right? So these are strings, and they're not going to be evaluated unless we use a special method right here. So this is where it gets a little confusing because we've got to know a little bit about object-oriented code. So what I showed you right now was like a scripting, but now we're going to instantiate a turtle object, right? So the first statement, import turtle, right? Turtle.turtle. That's instantiated. It's using the turtle package and instantiating a turtle object. So that turtle object is living inside your space, right? And that turtle object will do things. Since the very beginning. The other thing we need to know is we have color, and we're going to use these tuples. This tuple, a triple tuple. So red, blue, green goes from 0 to 1. It doesn't seem to take the actual string commands that the documentation leads you to believe it will. So we have to actually do that. Anybody think about how we might leverage this?
You could have different colors for different directions.
Yeah, good. And so we can do different colors for different directions or different colors for different states, right? So your algorithm might feed out numbers for those positions. Yeah, so that's where it gets a little bit interesting. Now, this object, now we bound the object to t, right? So anytime I call t dot, it's manipulating the object, it's manipulating the turtle. So t dot color, c, so I put in this tuple over here, and it's going to change the color that the object is tracking, right? So that's this color over here. Now I can put in my command list as I did before, and I said I wanted to make it to a square. It's forward 25, forward. Well, it's not quite going to do that, but we'll see. And then I can pop off these items. And here's something that's interesting. It's the evaluate command, right? So evaluate can take a string, t dot, and then the movement string, and turn it into a command. So that's how you can pass a string and turn it into a command, right? And then print as stops. And then this part over here is really important to get your control back. Otherwise, the thing will freeze. Honestly, I'm not too happy with it, but this is what you need to do. Turtle, tell turtle it's done. Tell turtle bye. And then if you accept it, you can pass it and get a terminator. But yeah, so basically you have to do done and bye, and then you can actually accept it. Try this out. So let's run it. So based on line. Now here's the important part, is I shut off this thread because otherwise it's going to lock down the system. It's also here. I don't think it's sometimes you need to force that thing to quit, but I don't know. Okay, so we can change the command list to make a red square. Pretty straightforward, right? We change red to 1, the others to 0, and then we change these commands, right? Forward 25, left 90, forward 25, left 90, right? So we're working in degrees. Degrees is default, but it also can change the radians, so you have to be careful. There, and then it's basically the code's exactly the same. So, and there's our little rover drawing a red square.
Hello.
Screen this time.
What's that?
The last left is unnecessary.
Oh, is it? Yeah. Yeah, okay. I'll cut it off. So now, because I would like to see the different line segments, right? Because if we're actually having to make decisions, if it goes in a straight line and does 3 different activities, it's better if I rotate the colors. So what we've done here is we've rotated the colors. And there's some code that's that we should probably point out. Okay, so we got this forward, left, forward, and the final turn. So we start with this over here, this tuple. But we've got a color change dictionary. This is just a very simple way to change the color. You might think of a better way to change the color. And over here we got one. So the dictionary basically maps keys to values, right? So if it's 1, make it 0.1, 0.5. If it's 0.5, make it 0. If it's 0, make it 1. So it's cycles the colors, right? And then we use this syntax over here. So I've got C, and I've got color change. We're using C index 0. So I'm using indexing the indexing syntax here, right? To change that tuple. So it'll essentially cycle this, right? Okay, so I'll just run that. And the cool thing about that is that you can actually see all the sides, right? It's going to get more important when it's doing random tumbles. Okay. So let's start with our algorithm, right? So we've basically made the mechanics. We've got it to move. We've got it to take commands. You can see it's probably stuck. But what I want to do is now make it do a random algorithm. So I'd like it to sample from random distribution and tumble around the screen, right? And then we can really get at some sort of behaviors. We are going to go towards modularization, but first what I do is I usually write this stuff in like a script, and then I add it. This one I'll change to an object-oriented paradigm. So if you're not familiar with object-oriented paradigms, we'll go through that as well. And I'll show you why that's important. You can see that the random library, import random randint, 1 to 360, so I'm tumbling between 1 and 360. This might be high, depending on how you want the behavior to hardwire. But basically, it takes a random integer from the distribution, right? And this is a uniform distribution. Yeah, so let's see. The other thing we can do is we can log of behavior. So this is also another important thing. So I think for these systems, it's really important to have a log of what happened, right? And then we can actually analyze later what happened and do experiments, write up some sort of analysis. So we'll do that as well. Let me just run it. So we'll look at the output, make sure we're having some random output. And you can see what I've done here is I've not evaluated anything, but I think it's really important to just use the cell system to see what's going on, right? So we can actually just examine this and say, okay, I'm going to execute t.left 141. It's the exact command that we need. We can troubleshoot it here, and we can see that it's actually making a random tumble and sampling from the distribution, right? So let me just point out some of this code as well, so that when you're actually coding it, you can see different pieces. Here's our behavioral repertoire, right? And this thing, to make it simple, I've only made it go forward. I've got the color change dictionary that I'm using, which is sort of inflexible. I've got a value, which is going to be the value, and I'm using the same value in this case for distance going and distance spinning, right? And then I have a behavior count because I don't want it to do too many behaviors and just tie on the machine. The move string has to be instantiated empty. Counter starts at 0, and then the max count is 25. We use the while loop to make the behavior happen autonomously, while counters less than max count keep on going, right? And then here's the sampling, right? So we've got values from random integer 1 to 360. Behavior number is from random integer 0 to 2, right? So that's 0, 1, and 2. But if I change that behavioral repertoire, obviously I'll change that sampling. And we can even change the distribution if we want to change the weights on the different behaviors, right? Let's see. And then here's your all-important killer code that kills it, right? So let's actually go to the next step and see what this one does. Okay, so this is actually a sample of Mars. You have that in the folder. And you can see what it's doing is the code that I told it to execute, and each time it turns, it has behavior, right? And it's randomly bouncing around, it totally ignores rocks, it doesn't actually have any awareness of where it is, and it can run off the screen, right? All those things are problems. But we've got something that behaves a lot more like an animal now. Maybe not a smart one, right? And let me point out the code for that. I should also point out that you can change the pointer to make it look like a Mars rover. I didn't get a good one, but you could do that if you want. But we did get the background fixed. So right now we have both, let's see, turtle.screen. So you instantiate the screen object, which is the thing that it works on. That's the thread I told you about, screen. And then we can take screen and give it a background pick, right? Attribute. Actually, this would be a function, a method, and then we would attach that background pick. We got the behavioral repertoire, and I think everything else is pretty similar to what I showed you already, right? The other thing that we have right here is we've appended a log, and I think this is really important. I see a lot of code written that doesn't log stuff, and that's really a shame because we all think about big data, we think about behavior, we think about user behavior, And if you're writing code that doesn't log what happened, right, how are you going to know what happened? So I just advocate that because honestly, it's kind of rare that people log their stuff. I mean, I know production code maybe does this, but when people are going through their work, it's important to start there. So anyway, log append, we can append a list of the values, and then we can print them out over here. So it should print out one if we want. Yeah, there's a log. Wasn't not. Okay, so now here's where we can really get to a point where we can start to make something that we can hand off to you guys, and you can really start plugging stuff in. And that's when we take this functional code, or actually it's just a script, right? So it's got no real modularization, and we're going to make it into an object-oriented piece of code that'll have different logical modules that we can swap in and out. So I'm essentially going to take the same code, make it object-oriented. Let me just go through that. So I can conceptualize one object as the behavior, right? So this is what you can think of as the brain. And what we do is we have a little doc string over here. It tells me what it does, right? It generates the next move based on the logic. It's got the self value. Remember, there's movement string, color, color change. Color, I thought, was a behavior because it represents state, right? We can introspect it to the object using the color as an output. And then the next behavior method, right? So we can instantiate random behavior, and it's going to sit there with these default values. And then we can ask it next behavior, and it uses its behavioral dictionary and its random number drawer to find out what's going to do next, right? So basically the value, and then it takes one of these items, right, from there. And I hope it's obvious. It should be very obvious to you where you can put the smart part in, right? This is random at this point, but it could be smart, right? Okay, and let's see. And then it changes the color change, right? So it's rotating colors here, again, sort of in a dumb way. I mean, it does tell us what the different moves are, which is obvious, but it could be a rainbow that it cycles through so you can see a gradient, or it could be to represent the internal state. I was told to go somewhere where I shouldn't, right? It may change color, so it might actually tell you something about what's going on inside. And then return, right? So return, we return the behavior, and we return the color, right? So when I call this object sits, and I say, give me a behavior, it's going to tell me a behavior with a value and a color. It'll tell me those two things, and I can actually have my turtle object just read those two, and then change. So that's going to. Let's see. I should say for the beginners or people who are not familiar with this type of coding, this is a little bit confusing to everybody's self. So when you think about an object, you think about it as a thing, like an apple, right? And each apple is different. And self will tell you apple number one, right? So apple number one has things like a value, movement, string, color at any given time. And that's, self pulls those things in, so features in when I say self. So if I say, okay, random behavior one, it'll pull in random behavior one state, right? So you can think of there's many behaviors or many instances of this object, right? It makes more sense with a turtle because it's less abstract, right? You may have 10 turtles running around, and they're all in different places, and that's their feature. Those are the features, right? So that's the self syntax. And then we can just look at this turtle object. So with just two objects, I can make a sort of a AI-ready ecosystem. So the turtle object over here, it has its own log, so the turtle knows where it's been, and I can actually, it holds on to that. Again, think about the apple. The apple goes places, and as it goes places, it takes a snapshot of wherever it goes, right, all the behavior it's been asked to do. It has a max count, so it's only, when I run it, it's only gonna run a certain number of times, just for sanity. It has a screen attached to it, right, so that turtle, it belongs to a screen. And then the behavior logic, it's right here. So what I'm going to do is I'm instantiate the behavior right here. So that's this, and it's bound to this thing called self-type behavior. Okay, and then there's the while loop. That should be familiar from before. It's just nested inside there. And this object is actually not that complicated, right? What happens when I tell it the turtle object, it instantiates this, and then it begins to behave. It doesn't even have any methods. It just starts up, gets all its values, and begins to behave. And as it's behaving, it just takes the behavior right here, right here. So it takes the thing that's already bound to it, so it's got a logic that's loaded up into it, and it says next, 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 next. So it just calls that behavior brain, and it keeps on saying next one, next one, next one. So
init is a constructor?
I'm sorry?
Init is a constructor?
It's an initialization constructor. So it's hardwired into the Python code, and basically what it does is when you instantiate the object, and it always runs. You don't need it to make an object, but if it's in there, it's the first thing that runs. So it stands for initialization. So I actually come from a, I should run that for you before I, oh. So that's the same thing. I made it a little shorter, and you can see, but this is based on the object-oriented code. I think it's more interesting when it's shorter runs. Okay. So I should say something about object-oriented coding. There seems to be some sort of ideas about what's good and bad, right, in coding, and like very strong feelings. So some people say this is the only way to code, right? And anybody else who codes in functional coding or scripting is just really not coding, and you got to do object-oriented coding. Other people say, functional coding is the only way to code, and anybody who's doing any other coding is really not coding, right? Because there's a lot of side effects. You know what's going on. You ask for a gorilla, you get a jungle, on and on, right? And I always tell people, like, if you think about it, like, just take a step back and think about coding a Pokemon game, right? You coded an object-oriented coding, right? Well, okay, we've got a Pokemon, okay, that's an object. We've got a board, that's an object, right? We've got a method, right? Pokemon fight, so two objects are fighting in the board. And they say, think about that in terms of functional coding. It's a lot harder, the paradigm's a lot harder. And if you can do that exercise with a lot of things in the world and think about like how different functional and object-oriented paradigms match to different coding styles, it's a really productive way to appreciate all different perspectives. I don't mean to be pedantic or whatever, but I just can't help it. Okay, so there's two other pieces that if I want you to do something intelligent, right, with this code, like what do we do? Okay, so you sort of got a scaffold right now. We've got a scaffold, we can put a brain in there. What else might you want to do if you want to build an intelligent code? So I'll just open it up to you guys. Like, well, what's lacking from that, right? It's sort of just a dumb thing with no brain, right?
So you want some sort of object avoidance. You have this Mars picture, right? You have giant rocks that you probably don't want to run into.
Yeah.
You want some way to avoid those.
Well, okay, so that's a big thing. How would you break that down into small modular steps?
So you would want some code to examine the space that your rover is following and see what the difference is, probably like gradients or image gradient in this case, as you step along.
That's cool.
That's where I am.
So we could take the Mars image and threshold it, right?
Yeah.
And anything that's black or anything that's white would be a no-no. Turn it to zeros and ones?
If you, at the basic level, yeah.
Or would you do bounded boxes?
That's a good question. I don't know. Probably start at something basic.
Okay. Cool. What else? What else would you guys do? So we need a map, right? We need some. So he's referring to the fact that our environment is structured. We need some ability to sense the environment, right? And one way to do that is to threshold the image, right? I've done a sort of a dumber thing, and I've just drawn. I've programmatically drawn squares on the board, right? I've used the size of the image and programmatically drawn squares, which I've showed you over here. But that's just because it's the first step, right?
Your way is much easier.
Yeah. But no, I think the image analysis tool is really flexible. But what else? What else do we need? So we need to know our environment, right? What else do we need? And you're talking about sensors in some way, more sensors. What else?
What are you looking
Yeah, what are you looking for? Are you okay? Good, good. So you're maybe what would you be looking for?
for? The worm was looking for salt.
Yeah, yeah. Okay, so maybe you have like, I don't know, metal deposits or something, right? Pure
Water
water.
was a big thing for the Mars exploration.
Yeah. Yeah, yeah. So you need to be able to tag those things maybe automatically, or maybe manually. I don't know, right? Okay, so we've got to have maybe attractors and things that we're avoiding, right? Now what else? What else do we need?
Frank,
Frame, oh,
just don't go upstream.
yeah, yeah. Okay, so the barriers are avoided. Yeah, yeah, yeah. There's something else that's sort of maybe it's too fundamental, right? It is.
Past behaviors.
Which one? Oh, past behaviors. Yeah.
You want
Well,
to, pretty much.
Yeah.
You want to follow the same path.
So experience, right? So you maybe we need a map, right? So we've got like a board that's the real world, and a map that's our approximation of the world. Good, good, good. Yeah.
Turns?
Is it
What about turns?
turns? Okay. What do you mean?
Not hitting the bound box and immediately turning left, coming like sort of curving towards the direction.
So what? Okay. Okay. Good. Good. So what do you? There's a few things there. I'm trying to unpack.
I'm guessing probably the speed that it's going at,
Uh-huh.
the direction it's going towards, and figuring out which direction it needs to go after so it turns towards that direction.
So are you thinking about foresight, or are you thinking about reactive reaction? Right. Those are two different things. I think the way you said it, it's almost as if you have a look forward, right? Like you know there's an object and you're turning away from it, right? So you need ability to project your next behavior, right? Oh yeah, sure. Type it in. My secret code. I used to have a professor who always tell us his secret code when he typed it in. It was something like his cat's name. So everybody knows. All right, so yeah, so basically what we've done over here is we built the board, and I've used functional programming over here. So build board, pass in the usable range, right? The board, I'm using something called NumPy, if you guys are familiar with NumPy. Anybody know what NumPy is? It sounds like everybody knows what NumPy is. Yeah, go ahead.
Numerical, mathematical package.
And why is NumPy special?
Because I think it's highly optimized.
Oh, that's right.
Here in Austin.
Yeah, that's special, yeah. And why does it suck? It's only arrays, right? Single object type. So again, it's good for some stuff and not good for others. It's really good for this because I can just make an array of zeros when I'm done. And array of zeros where you can go, right? So I can go there, and then I can add boxes as a ones, and then I know, I already have a map, right? Like a square map of zeros and ones. But it's not a data frame, right? It's not like a pandas data frame that's got rich expressivity. So very fast. So you can see some of the code over here. So I've got board I0 to I1. So what I've got here, okay, let me unpack this a little bit. Right, because I haven't passed in the object. That doesn't make any sense. So we'll just, because I've made the function over here, and I've actually used it over here. So I've got the width and the height coming in using this tuple assignment, get Mars image size. It's just a package you probably have to load or install, right? And it takes the width and the height, you can print the width and height, and then it makes a usable range tuple, right? Obstacle range, and I've just used this list of lists construction over here. So I've got 0 to 50, 0 to 50. This is the width, 0 to 50. The height 0 to 50, so it's a 50 by 50 box up in the corner, right? And I've got a number of obstacles, so a list of square obstacles. It's really kind of dumb, but you should, as this gets coded, you should be able to see the object reacting to the boxes or avoiding. And then board, and then build board, usable range and obstacle range. So this function takes in both usable range, which is the square, right? The obstacle, the size of the image, and then the obstacles, which is a list of obstacles. And we use a for loop over here. Again, forgive me, this is really basic, but I want to make sure everybody's with us. For ion obstacle, so this will iterate through the obstacle, right? Each obstacle, unpack it, and then map it to the board. And what it does is it takes the beginning width to the end width, beginning with height to the end height to the square size, and adds 1 to all of these. This is the plus 1, right? So it just makes one where you've got an obstacle, right? You could make the bounding optional, so 1's around the edge, so that you can ask it for forcing. So that's the code to give it an ability to, well, it's just building 2 maps, right? 2 maps, the learn map and the map that's actually the physical world. Check position, I've used pass, right? So that means that there's no code there written, but you might want to pass in like X position, Y position, board, and learn map, right? So the 2 things that I built, plus the actual position of the individual, and then maybe use some conditional or something here to pass back if I should go there or not, right? So there you get to the foresight. I like your idea of the curve because we might want to know how much we're checking, right? How often are we checking? Do you issue a command and do you check if it's okay? Or do you just run over there and bump into something, right? That's a decision you have to make. And then spatial awareness, so we also talked about this. So I guess I'll run this code. And you can see the array right there. It's got, in this case, it's an array that's already got obstacles added to it. So these are places you can go, and these are places you can't, and that's the physical world. If I looked at the other array, it would just be empty because the tabula rasa, right? The rover doesn't know anything yet until it starts bumping into things, the way I've set this up. And then spatial awareness is the last thing. So this was actually the hardest part I found in code because it involved a little bit of trigonometry and it also involved like what I found somewhat complex quadrant system because everything is, as you spin these triangles around, you know, they get all disoriented. So stick with quite a while in code. But well, I'll just run it and show you what it does. So as it's going through, it tells you where it's going, right? And we can look at this. This is a quadrant on a Cartesian coordinates, quadrant 4. I'm going to execute t backwards 56. And backwards is obviously not the way I pointed, right? So it's the quadrant that's opposite. I'm located at 0, 0, 0, 0, facing 126 degrees. My angle is 36. Adjacent side of the triangle is 45. Opposite side is 32.92. And I'm going to move 56 positions. I will arrive at negative 32.9 and 45.3. And then we want to check and see if this works, right? 32.9, 45.3, so it's accurate, at least in this step, right? I'm going to execute backwards 81, and where am I going to arrive? Negative 14.22. Did that work? There's a problem right here, right? So that maybe needs to be a little hammered on. But the thing about this is it actually has the ability, or potentially the ability to know where it's going to go and be right about it, right? So it can compare that to its internal map. So that's where I leave this, is we've got all the pieces, and we have a tumbler that tumbles in an environment. We have 2 maps with the ability to have foresight. So where do you go with that? And that's where the workshop starts. or ends, you go home and hammer on this. But that's the whole thing.
So none of the rivals
Let's see. They happened at home when I came before. So this might be the old code. If the thing that happened before is happening again, was 2 of them were right and 2 of them were wrong. I think it's
wrong.
this is right. First measurement.
I will arrive at negative 32. I located at 32. Completely wrong.
Yes. No, so this did work right before that. Right here. But yeah, it's just a matter of choosing a quadrant. There's some systematic. Trigonometry doesn't work.
Clearly the math is broken.
Yeah. I think I transposed sine and cosine or something like this. But yeah, it was a little hammer. Let's see what else. And those are the steps. Let's see what we got. Yeah. Now, if you will, if you want to code, change this into something interesting. You should have the notebook, and you've got everything up to the point where I showed you.